Good morning, guys. Today we will see next problem for truss element, okay, or for truss structure. We will solve next problem, okay. As we discussed how to solve or what are the procedures to apply to solve the truss problems. We get displacement, stresses, and reactions for this truss structure. We have applied our standard procedure, which means first we need to create the elemental stiffness matrix. This is your first step. Then second step is what? Construct the global stiffness matrix. Then third step is what? Apply the boundary condition. Then by applying the boundary condition, apply the elimination approach. You will get the displacement first. Then next you will get the stresses by using these displacements, and finally you will get the reactions by using these equations. Okay. So here the same problem, and this problem is asked for 12 marks. This problem actually it is asked for 12 marks in end semester examination. So we will try to solve this problem. Okay, so in this problem there are three members, first, second and third member. So length is given between node 1 and node 2. This is node 1 and node 2. So length for this element, first element, it is given equal to 4000 mm. Then for second element, length is given equal to 3000 mm. Means between distance between node 2 and 3 is given equal to 3000 mm. And distance between this first and second node is 4000 mm. Okay, now, so this is first element, this is second element, and this is your third element. Then at third node, the forces, applied forces are given. This 20 kN, it is applying in a downward direction, and this horizontal force of 15 kN, it is applying at node 3. Okay, so 15 kN horizontal force is given and 20 kN in a downward direction. The vertical force is given at node 3. Then at first node it is fixed over. In second node it is also fixed over, but it is there is a nodal support. Okay. Then next is what? Young's modulus value. It is given common to all these three members. It is equal to 200 gigapascal. So actually the forces are given in kilonewtons. This force is also given in kilonewton. So we will convert this E value in kilonewton per mm square. So it will become equal to 200 kilonewton per mm square only, because 200 gigapascal is what? 200 into 10 raised to power 3 megapascal. Now 1 megapascal is what? 1 Newton per mm square. So it will become 200, this 10 raised to power 3 is nothing but kilo. So 200 kilonewton per mm square. So this E value, it is equal to 200 kilonewton per mm square. And this area is equal to also given for all three members. Area is also common, which is nothing but 2000 mm square. Okay, so all the data is given. Now we need to proceed the same procedure that we have applied in our previous lecture. Okay, to solve the truss problem. So to solve the truss problem, we need to construct first one table for each element, as we have constructed one table in previous example also. So first we need to create one table. Means element. Why we need to create this table? Because we know this elemental stiffness matrix. Elemental stiffness matrix K is given in terms of L square Ln minus L square minus L, where L is nothing but your cos theta and L is nothing but your sin theta. So theta, we need the theta value for each element. So this is your first element, this is your second element, and this is your third element. So for this we need to construct, we need to get first coordinate system, global coordinate system. So at node 1 it's selected as a reference node, and at this node this is your global coordinate system xy. Okay, so and according to this global coordinate system, we need to find out our theta values for each element. So first element, this is your second element, This is your second element, and this is your third element. So from reference axis, what is the inclination of that element? We need to find out. Okay. The next, so for element, as there are three elements, so we need to find out the values for these three elements. Element 1, 2, 3. Then we need to find out the lengths of each element. So L1 is equal to what? L2 is equal to what? L3 is equal to what? So first, for element 1, for this first element, length is equal to 4000 mm. It is given. So L1 will become 4000 mm. Then L2 is also given 3000 mm. L2 is also given 3000 mm. Now L3, we need to find out this L3. This is L1, this is L2, and this is L3. Now by using your Pythagoras theorem, you can find out L3. So L3 can be determined. L3 square is equal to L1 square plus L2 square. So L3 will become square root of L1 means 4000 square plus 3000. So you will get L3 as 5000 by using Pythagoras theorem. So L3 will become 5000. Okay. Now next is what? Theta values. So next is inclination. So theta 1 is what? Theta 2 is what? And theta 3 is what? Okay. So theta 1. This element, for this element we need to find out theta 1 with respect to this reference axis x. So this element, it is parallel to this x axis. Okay. So this theta 1 will become equal to 0 because it is parallel. So it is making a 0 angle with this reference axis. So theta 1 is equal to 0. Then theta 2 for this second element. So second element, it is inclined to this x axis with 90 degree. So theta 2 will become 90 degree. Okay. Then theta. Now this third element, it is inclined to this x axis by what angle? Is nothing but your theta. Okay. Because first node we have taken as a reference node, and at this node we have applied our xy coordinate system. So from this x axis, what is the value of this theta 3? Because at what angle this element is inclined to this x axis? So theta 3 will become, to find out theta 3, as we know that theta 3, if we use the tan theta relation, so tan theta 3 is equal to front side divided by adjacent side, because this is rectangle. So front side by adjacent side. Front side is 3000, adjacent is 4000. So 3000 by 4000. Okay, it means theta 3 is equal to tan inverse of 3 by 4. So tan inverse of 3 by 4, it becomes theta 3 is equal to, I think theta 3 is equal to 36.86. 36.86. Okay. So this, in this way you will get theta 3 value. Now next is what? So theta 3 is equal to 36.86. Next is what? L. Small l values for each element and small n values for each element. So L is nothing but cos theta. So find out L values. So this becomes L1, L2, L3. So cos 0 is nothing but 1. Cos 90 is nothing but 0. Cos 36.86. Now cos 36.86, its value is equal to 0.8. active point 798 is the value for this cos 36.86. So I am taking this the round figure value as point. Similarly, we need to find out next m. L is nothing but your cos theta. M is nothing but your sin theta. So m1, m2 and m2. So sin 0, 0. Sin 90 is equal to 1. Okay, and sin 36.86, it is equal to 0.6. Okay, so in this way you will get L and M values. Now next is what? We need to find out also L square and M square, because our elementary stiffness matrix consists of L square, LM, M square, all values. So we need to find out this L square, M square and LM. So L square will become, and this M square will become. So L square, M square. So L square will become this square 1, 0 and point x square is 0.64. Similarly, M square will become 0, 1, 0.62, 0.36. Okay. So in this way you will get L square, M square, and finally we need to find out LM also. LM for first element will become L into M, 1 into 0, 0. L into M, 0 into 1, 0. And 0.8 into 0.6, 86, 48 means 0.40. 0.40. So in this way, you will get this table. And because this table is used to construct the elemental stiffness matrix for each element. Because we need this table to construct our elemental stiffness matrix for each element. Now, next is what? So by using this table, now we will construct our global stiffness matrix. First, we need to construct the elemental stiffness matrix. So elemental stiffness matrix for first element. We need to construct our elemental stiffness matrix for first element economy. So as we know that E is equal to 200 kilonewton per mm square, and area is equal to 2000 mm square, and it is common for all elements. So now we will construct our first elemental stiffness matrix. So first elemental stiffness matrix K1. So we know that the standard elemental stiffness matrix for truss element, it is given by. So first we need to write down this standard elemental stiffness matrix in terms of L square, M square, Lm. So first this elemental stiffness matrix is given by L square Lm minus L square minus Lm. M square minus Lm minus M square. L square M square. So Lm minus Lm. Lm minus Lm and minus L square minus M square, and this is minus. Okay. So this is your standard elemental stiffness matrix for truss element. Okay. This 4x4 matrix, it is. Why it is 4x4? Because at each node there are 2 degrees of freedom. we have derived this elemental stiffness matrix for our truss element by using this global coordinate system as well as by using the degrees of freedom concept. Okay, so at each node there are 2 degrees of freedom, vertical as well as horizontal. So due to this, it will become a 4x4 matrix. Okay, so by using this, now we will construct our first elemental stiffness matrix. Okay, so K1 will be K is nothing but A by L into this matrix. Okay, A by L into this matrix. So you will get first elemental stiffness matrix. So first elemental stiffness matrix means A1 E1 by L1 into. Now we need to place this L square Ln minus L square Ln values in this matrix. So for first element, what is L? For first element, what is L square? So L square is equal to 1 from this table for first element. Then Lm for first element, Lm is equal to 0. Then minus L square is equal to minus 1. Minus Lm is equal to 0. Then Lm is equal to 0. M square is equal to 0 also. Then Lm is equal to 0. M square is also equal to 0. Then L square is equal to 1. So minus L square minus 1. Lm 0, L square 1. Lm also is equal to 0. So Lm 0, this 0, 0, 0. So this is your first elemental stiffness matrix. Now we need to first find out this A, E by L value. So A is equal to area is equal to 2000, E is equal to 200, E is equal to 200 divided by L1. L1 is what? 4000. L1 is equal to 4000. So this will become 1, 2, 3, 1, 2. So it will become 100. Okay. So this value will become equal to 100 into. So finally this will become, instead of 1, by multiplying this 100 to this matrix, it will get only at this 1 values there will be 100. So this will become 100, this will become minus 100, this will become minus 100, this will become 100. Okay. So in this way you will get your first elemental stiffness matrix K1. So K1 is equal to 100, 0 minus 100, 0, 0, 0, 0, minus 100, 0, minus 100, 0, 0, 0, 0, 0. Okay, this is your first elemental stiffness matrix. Okay. Now similarly, second elemental stiffness matrix K2. K2 is equal to, so second elemental stiffness matrix K2. K2 is equal to K2 E2 by L into this matrix. Now L square for second element. For second element, L square is what? L square is equal to 0. Then Lm is what? Lm is equal to also 0. Then L square is 0. Lm is 0. Okay. Then Lm is what? Lm is 0. M square is what? For second element, M square is 1. Lm is 0. Minus M square is 1, minus is minus 1. Then L square 0, Lm is also 0. L square is also 0, L is also 0. Minus Lm is 0, minus M square. Minus M square is 1. So it will become minus 1. Then 0. Then M square is equal to. So in this way, the second elemental stiffness matrix will, we can determine the second elemental stiffness matrix. So K2, for this we need to find out. Now this value is what? A2 is equal to area is same. It is nothing but 2000 m square into E is also same, 200 divided by L2 for this element. L2 is equal to 3000. So if we solve this, you will get 400 by 3. 200 into 2, 400 by 3. It is equal to I think 133.3. 133. So this will become equal to 133.3. Now by multiplying to this matrix, only these elements will change. 133.3 minus 133.3 minus 133.3 133. So this is your second elemental stiffness matrix. Okay. So first elemental stiffness matrix, here we will write your first elemental stiffness matrix. So K1 is equal to 100 0 minus 100 0 minus 100 0 0 0 0 0 minus 100 0 100 0 0 0 0. So this was your first elemental stiffness matrix. Similarly, you will get K2 as K2 is equal to 0 0 0. So this will become 0 0 0 0. Then 0 133.3 0 minus 133.3 0 0 0 0. Then 0 minus 133.3 0 133. So in this way, this is your second elemental stiffness matrix. You will get the first element. This is your first elemental stiffness matrix. This is your second elemental stiffness matrix. Now similarly, we will find out third elemental stiffness matrix. So for third elemental stiffness matrix, K3 is what? A by L means A3 by L3 into this matrix. Now for third element, L square is what? For third element, L square is 0.60. Lm is what? Lm is 0.40. Then minus L square is minus 0.60. Minus Lm is minus 0.40. Then Lm is what? 0.40. M square is what? M square is 0.36. Then Lm is what? 0.40. But this is minus 0.40. And minus M square is what? Minus 0.36. Then minus L square means minus 0.64. Minus Lm means minus 0.48. Then L square is what? L square is what? 0.64. Then Lm means 0.48. Then minus Lm is minus 0.48. Minus M square is minus 0.36. Then Lm is 0.40 and M square is what? 0.36. Okay. So in this way you will get your third element. So you cross check whether this matrix is symmetric or not. So this is your diagonal. So 0.48 minus 0.48, 0.48 minus 0.48, 0.48 minus 0.64 minus 0.36, 0.64, 0.36 minus 0.48 minus. So this is symmetric, means it is correct. Okay. So now we need to simplify this value. So area is 2000 into E is 200 divided by L3. Now L3 is what? 5000. So this will become equal to 1, 2, 3, 2 into 2, 400 by 5. So it will become 80. Okay. This will become 80. So multiplying this matrix minus 80. 80 into this matrix. So now we need to here multiply for each value by this 80, so that you will get the final elementary stiffness matrix. Okay, so we will write this matrix here. Okay, so this matrix, instead of this we can write this matrix here. No need to write this matrix. So now we will write down this third elementary stiffness matrix here, K3. So by simplification, on simplifying means by multiplying this value, all these values, you will get your stiffness matrix as K3 will become 51.2, 38.4 minus 51.2 minus 38.4. Okay, then 38.4, 28.8 minus 38.4 minus 28.8 minus 51.2 minus 38.4, 51.2, 38.4 minus 38.4 minus 28.8, 38.4 and 28.8. So in this way you will get third elementary stiffness matrix. This is your third elementary stiffness matrix. So in this way you will get third elementary stiffness matrix. Okay, so now this use of this table is over now. So we can use this space to construct our global stiffness matrix. Okay, this table we have constructed to determine the elementary stiffness matrix only. Now we will use this space for global stiffness matrix. So up to this clear? So this is your first elemental stiffness matrix, second elemental stiffness matrix, and third elemental stiffness matrix. Now we need to write down the connectivity of that elemental stiffness matrices also. So your problem is like that. This is your problem. So for first element, you know displacements are U1, V1. For second node, you know the displacements are U2, V2, and for third node, displacements are U3 and V2. Okay, so the first element, the connectivity of this first element is in between node 1 and node 2. It means between U1, V1, U2, V2, rows and columns. So we need to write down this connectivity for first element. So first element is in between U1, V1, U2, V2. U1, V1, U2, V2. Okay. So this is the connectivity of first element. Similarly, the connectivity of second element is in between node 2 and node 3. It means between U2, V2 and U3, V3 displacements, means between rows and columns. So U2, V2, U3, V3. For second element, the connectivity is between U2, V2, U3, V3. U2, V2, Why we are writing these connectivities? Because during our construction of global stiffness matrix, we need to know the connectivity of that elemental stiffness matrix. So we need the connectivity during our global construction. Okay, during our construction of this global stiffness matrix. Similarly, this third element, the third element connectivity is in between node 1 and node 3, means between displacements u1 v1 and u3 v3, between these rows and columns. So this was your first, second and third element. So write down the connectivity of this third element stiffness matrix between u1 v1 u3 v3, u1 v1 u3 and v3. Okay, so these three elemental stiffness matrices we have written here. Also we have written their connectivities. Okay, now by using these three elemental stiffness matrices, we will construct our global stiffness matrix. Okay, so up to this clear. Now try to solve this global stiffness matrix, or try to construct the global stiffness matrix by using these three elemental stiffness matrices. Okay, and I will construct this global stiffness matrix in your next lecture. Up to this it is clear, and I will conclude this lecture here only. Okay, thank you.